Next up, we want to talk about the normalization and orthogonality of the wave functions for the particle in a box. What we're going to have to do is we're going to have to solve for this constant b. Remember that if the wave function to be properly normalized, we have to have 1 equal to the integral over all space psi star psi d tau. In this case, the function is real, so I don't have to worry about complex conjugates. My coordinate is only the x-coordinate, and all space is only 0 to a. So this is equal to psi squared of x dx, or equal to the integral from 0 to a b squared sine squared n pi x over a. Rewriting, reorganizing, what I end up with is that 1 over b squared, separating this out and dividing both sides by it, is equal to the integral from 0 to a sine squared n pi x over a dx. Remember my dx here. What I'm going to do now is look up at an integral table. When I look at an integral table, I find that the integral of sine squared bx is equal to 1/2 x minus 1 over 4b sine 2bx. I'm going to substitute, so small b is equal to n pi over a, and I have to evaluate from 0 to a. So this is equal, so my integral 1 over b squared is equal to 1/2 x evaluated from 0 to a minus 1 over 4 n pi over a minus, sine of 2 n pi over a x. Again, evaluated from 0 to a. This term will give me 1/2 a minus 1/2 0, or a. Rewrite this to make it clear that it's an a. What will this term give me? Let's not worry about the front, we'll write it in. So 4a over n pi sine 2 pi a over a minus sine of 0. Well, the a's cancel. I'm left with sine 2 pi, which means that this is 0, this is 0. The result, I should have written this as a over 2. The result is that 1 over b squared is equal to a over 2. In other words, inverting both sides, b squared is equal to 2 over a, or b is equal to the square root of a over 2. The next thing I need to do is show that these are orthogonal. Okay, my next point is orthogonality. And what orthogonality says is that the integral from 0 to a of psi m psi n dx must be equal to 0, where n is unequal to n. I'm going to leave one piece of this, but one thing I want to introduce is the idea of symmetry. So I'm going to draw out my functions. So here's a picture of my n equals 1, and then here is n equals 2. N equals 1 is what we call a even function. Namely, if I draw a line, the center, if I have a center of symmetry in the system, which I do right here, if the value of psi on one side is exactly equal to the value on the other side, equal to, then this is an even function. On the other hand, if I look at n equals 2, what I see is that this is what we call an odd function. Namely, that the wave function over here is equal to the same value as it is over here, except that it's the negative. Now, where can I use this? Anytime I have an integral such that I have my total integrand is odd over all space, the value of the integral is 0. So what we'll see is that and even and odd functions have a property just like numbers. A even times an even will be equal to an even function. Even times an odd will be odd. And odd times odd will be equal to even.